Right. So in this video, I want to talk about polar and Cartesian geometry or coordinates, I guess, and go through the geometry of a circle and kind of go back and forth between different variables. So I have a circle here, and I'm going to go ahead and let this be of radius r as usual. And for right now, just because I don't want to fiddle with it, let's imagine we measure angles from the positive x-axis. Now, we are going to define angles such that positive angles follow the math convention. So positive angles are rotations which are counterclockwise. Negative angles correspond to angles which are clockwise. So there's that. And what I want you to see is that there's a relationship between the distance traveled along the edge of the circle and the angle that is swept out. So as an object moves along the edge of a circle, there's an angle that's swept out and a distance traveled. This distance is, okay, so what could the relationship be? Well, I know that if you go all the way around, the angle would be 2 pi radians, and the arc length would be the full circumference. So when S is equal to 2 pi r, theta would be 2 pi. Oh, yeah. And then if I only went halfway around, well, that would mean that the arc length was pi times r, and the angle would be only half as much, it'd be pi. And if I went a fourth of the way around, it'd be, well, it'd be pi over 2 r is the distance traveled if you went a fourth, 90 degrees. And the angle would be 90 degrees, or that's the same as pi over 2. So hopefully you can kind of see there's a connection between the distance you travel around the circle and the angle that is swept out as you move around the circle. That's the main utility, or one of the main useful features of working with radians, is that you get the simple relationship. If you work with degrees, you have some extra conversion factor to deal with. So what we find in general is that whatever the angle is, the arc length it corresponds to is the angle times r. So in general, we have that S equals theta in radians times r. Okay, so that is generally true when you're moving around a circle. Now, we can do calculus. So, well, I can take a derivative of S with respect to time. So that would be the rate of change of position along the edge of the circle. Well, that's just going to give me the tangential velocity, the velocity as I go around. So the derivative of S with respect to time is going to be my tangential velocity. The derivative of r is 0 because r doesn't change. And so what I find is that the tangential velocity is related to the derivative on the angle. So in particular, we find that V tangent equals theta dot times r. Okay. And this quantity, so there's an analogy between positions on the circle and angles, which means that this quantity, theta dot, is analogous to positions, but not positions in space, but sorry, not sorry, it's analogous to velocities, but not velocities in space, but in velocities in angles. So we call this quantity angular velocity. So this quantity, theta dot, is defined to be Greek letter omega. It's not a W. Don't say W, you'll get confused with other quantities. It's omega, lowercase omega, and it's called, it has different names. People call it angular velocity. Sometimes people call it angular frequency. I'm sure it has some other names. I'm just not thinking of them right now. The units of this new quantity, well, it's an angle over time. That's going to be radians per second. Okay, so omega is the time derivative of theta. It tells you how many radians per second you gain every second, or sometimes it's called angular velocity or angular frequency. So you can write this formula as saying that V tangent equals omega times r. All right. So that's a useful kinematic variable. So we rather than describing positions along the circle, we can describe what happens in terms of an angle, but then that means we need to be able to convert rates of change of positions into rates of change in angles. And in physics 1, I usually call it angular velocity. When we talk about light and optics, I usually call it angular frequency, but it amounts to the same thing. Okay, so just like you can take if you can take one derivative, you can take two derivatives. So omega, I should also say this. So omega, remember, positive theta meant positive or meant counterclockwise. So omega greater than 0 means counterclockwise rotation. Omega less than 0 means clockwise rotations. And I'll be honest, I don't have tons and tons of intuition about it, other than a few standard cases. So let's do an example. Let's imagine we had a record which is spinning at a constant 7,200 RPMs. So it turns at 7,200 rotations per minute. And that's really a frequency kind of thing. But we know, because it's all steady motion, we know that every turn, every cycle corresponds to a 2 pi change in the angle. So basically what I'm saying is this gives me, well, let's see here, that would be 7,200 turns per minute times 1 minute over 60 seconds. And that's going to equal 120 turns per second. Okay, so this would be rotating, if that was true, this would be rotating at 120 hertz. However, since I know that each turn corresponds to a change in angle, and it's basically 1 to 1, so, or not 1 to 2 pi to 1, I know that each turn corresponds to 2 pi radians, so I can then deduce that omega must equal 120 times 2 pi, and it would have units of radians per second. And all right, so 240 pi. You could multiply it out if you wanted to. So that's an example, and you know, I'll be honest, I don't have a lot of intuition. I know what it looks like to see something moving at 5 miles an hour or 10 meters per second or 30 meters per second. I know what that looks like when I see it. I don't know this. I don't have enough experience in my everyday life just to look at something and just guess a frequency. But if you were to talk to a machinist or someone who does a lot of rotational things, I'm sure they would be able to just look at it or maybe even listen to it and know the frequency or the angular velocity. One other little thing I want to say is if and only if, I'm a little hesitant to even say this, but if and only if the frequency or omega is constant, then you can define a steady frequency and you can say that omega is 2 pi times a frequency, which is the same as 2 pi divided by the period. Okay, now that's only true if omega is constant. If omega is not constant, then your rotation isn't steady, in which case it doesn't make sense to talk about a frequency or period in the first place. That only makes sense if it's a cyclic pattern where nothing changes after one cycle. All right, so that's a useful thing to know. All right, so next up, well, I just kind of alluded to it just a moment ago. If the angle can change in time, and in general, omega, the angular velocity, can change in time. You can go around faster and faster and faster, or you can slow down as you go around. Then we should not only look at the first derivative of position to get velocities, we should look at second derivatives to define some sort of an acceleration for rotational things. So, so if we had a tangential velocity that was changing, we could take a derivative on that. And we just said that the tangential velocity was omega times r. Now on the left-hand side, this is nothing other than the tangential acceleration that we saw in the last video. And when I take that derivative, this becomes omega dot times r. So kind of keeping with the analogies, when instead of positions, we had angles. Instead of velocities, we had angular velocity. This is an acceleration. We're going to call this the angular acceleration. So we're going to define omega dot to equal angular acceleration. We're going to give it its own symbol. And you might notice that with linear things, we tend to use Latin characters, and for rotational things, we tend to use Greek characters. And instead of A for acceleration, we're going to use alpha, Greek letter alpha. It's not a fish. If you call it a fish, everyone's going to make fun of you, so don't do that. Okay. Alpha is the what we use to represent the angular acceleration, and it represents the rate of change of the angles. It's basically measures how much are you spinning, are you rotating at a steady rate, at a constant rate, or is it going faster, 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 or slower, slower, slower? This thing's going to be the quantity that torque affects. Okay, so the units on this, the units on alpha are radians per second squared. So instead of meters per second squared, it's going to be radians per second squared. And then kind of going back up here, my formula that I have is that A tangent equals R times alpha. Just plugging in here for omega dot. And that's a good formula to know. Okay, so this allows us to go back and forth between, I said Cartesian, I should have said linear, but that's okay, between linear quantities and rotational quantities. We have that S is R times theta, that velocity tangent is R times omega, and acceleration tangent is R times alpha. Kind of pull this together with things we saw in the last video, and where we saw that, so we have, let me write these up here. We have theta equals S equals R times theta. V tangent equals R times omega, and that A tangent equals R times alpha, where theta dot is omega and omega dot is alpha. Okay, so one place where we can use these relationships is to go back to our case of an object which is rotating, maybe with some radius. And remember, I said, oh, okay, as you go around, you have some, you're at some point, and your velocity tangent might be there, and you'd have, so basically, or sorry, your acceleration tangent might be here, and your acceleration radial might be there. You've got both components, and I said that the formula for the magnitude of the acceleration was the square root of A tangent squared plus A radial squared. Well, we can rewrite this in terms of these new angular quantities, because the radial acceleration is going to be V squared over R. So let me write this out here. This is going to be square root of, that's easy, R alpha quantity squared plus V squared over R. That's R omega squared divided by R squared. Just plugging in there. And you can clean this up a little bit. This gives me R times the square root of alpha squared plus omega to the fourth. Got that right. So it'll be R omega squared. Yes. Okay. So that's kind of a little handy formula you might have or might want to solve for the acceleration. So this is the linear acceleration, not the tangential acceleration or radial. This is the total, the magnitude of the total acceleration. And you can relate it to all these same quantities. No surprise, just because you can relate velocities to the angular variables, so therefore, and accelerations to the angular variables, well, then everything we've done before can be rewritten that way. Okay, so just a nice little formula for that. Notice this stuff right here. This is very, maybe, hopefully, familiar. This says that the derivative of angular positions gives you angular velocity, and the derivative of angular velocities gives you angular acceleration. Those are the same kind of relationships we had between position, velocity, acceleration way back in week number 1. And that means that every problem we did way back with kinematic equations can be reworked in terms of angular quantities. So for example, I can take this equation and let's focus on the case for constant alpha, okay, where alpha is a constant, uniform angular acceleration. If that's the case, I could take this equation and integrate it, and I would find that omega of t equals alpha times t, remember alpha is just a constant, plus a constant of integration, and I need that to be the initial angular velocity. I want you to stare at that and think about it. Have I seen that before? Absolutely you have. This is just kinematic equation 1 rewritten with angular variables. So this is just going to be rotational kinematic equation number 1. And rotational kinematic equation number 1 looks just like kinematic equation number 1, except you use angular velocity, angular acceleration, and angular velocity there. Everything's the same. Similarly, we could look at, well, once we have this, we could go back here and look at this equation. And we could look at theta dot, and we could integrate both sides of this. So we would get the change in theta equals the integral of omega say 0 to time t. Well, but that's nothing other than 1/2 alpha t squared plus omega initial times t. Or rearranging that, I can say that theta as a function of time equals the initial angle plus the initial angular velocity times time plus 1/2 the angular acceleration times time squared. That hopefully looks familiar to you. That's nothing other than the rotational version of our kinematic equation number 2. So we're going to call that rotational kinematic equation number 2. All right? And no surprise that because the relationships between these are really mathematically the same as all of our old 1D kinematic equations, basically all you have to do is change the spelling from linear quantities to angular quantities, and everything goes straight through. The same is also true with kinematic equation 3. There's a rotational kinematic equation 3, which just says that, well, maybe I'll write it here on the board. I won't derive it, but it's no different than what we did way, way back, which says that omega squared equals omega initial squared plus 2 alpha delta theta. And this would be rotational kinematic equation number 3. Okay, so we've introduced these new angular variables, but they're really defined in a very analogous fashion to what we saw in the first weeks of the course. And so it shouldn't be much of a surprise that you get kinematic equations which mirror what we saw way back then. Let's do a problem, and then we'll stop this video. All right, so let's imagine we have a circle. Let's give it a radius of 5 meters, something a little different than 1. And let's imagine that we have a particle or a boat or something, it doesn't matter what it is. Initially, it's moving up with a tangential velocity. The tangential velocity, and let's say it's at 3 meters per second. Okay, so that would mean that every moment in time, as it follows this circle, it's gaining angles. So that's going to mean that omega will be positive because it's rotating counterclockwise. However, let's imagine that alpha equals -4 radians per second squared. Let's just go through and find everything just to see how it all works. So let's find, so this is at t equals 0. This is the initial tangential velocity. Let's find omega initial. Let's find omega as a function of time. Let's find theta as a function of time. And then let's use these formulas to find the magnitude of the acceleration at time equals, I don't know, 2 seconds. Okay, so that's what we want to do. Let's go through that. Omega initial. Well, to find the initial value of omega, I have to think about what it means and how it's related to what's in the problem. And this is going to be the useful fact. I know that V tan equals R times omega. And so at time equals 0, the tangential velocity is 3 meters per second. The radius is 5 meters. And this would give me omega at time 0. And I get that omega at time 0 is just going to be 0.6 radians per second. And it'll be positive because it's counterclockwise. I'll be honest, for a lot of these problems, I just look at it, and if I see that it's moving clockwise, then it's a negative angle, and if it's counterclockwise, it's a positive angle. All right, great. Now, that gives me omega initial. This is a constant acceleration, so then I can immediately use rotational kinematic equation 1 to find omega of t. So omega of t is going to be my initial omega, 0.6, plus alpha times t, so that's going to be minus 4 times time. And it'll come out as radians per second when it's all done. Okay, fine. Why don't I go ahead and evaluate this to say that omega at 2 seconds is going to be -8 plus 0.6, that's going to be -7.4 radians per second. Okay. And then finally, we want theta as a function of time. Well, if we know omega is a function of time and alpha is a constant, we can use the second kinematic equation to get theta as a function of time to tell me that theta as a function of time, let's say it started out at 0, is 0.6 radians per second times time minus 1/2 alpha, which was, sorry, the minus sign came from the minus sign in alpha. So it'd be minus 1/2, and we get 4 radians per second squared times the time squared. Great. So that gives me everything there, and all I need to do is find the magnitude of A. And remember, I had that handy formula. The magnitude of A was just going to be R times the square root of alpha squared plus omega to the fourth. Well, at time 2 seconds. Well, alpha is always -4, so that's just going to be, and R is 5, so that's going to be 5 times the square root of 16 plus 7.4 to the fourth. Good God. Well, let's see here. 7.4 squared. Oh, it's got to be pretty close to 56. And then I want to square that. Well, all right. You can multiply it out. This would be 7.4 to the fourth. And you have to take a square root. Unfortunately, I don't have a calculator on me, but that's what you would do. Okay? So that's how you use rotational kinematic equations. They're really just like you would do with position, velocity, acceleration stuff way back. It's really the same basic method. It's a little weird because these are rotational problems, and so people, and it's harder to have an intuition. I don't know. If you get if alpha is 407, is that reasonable? Yeah, it's hard. It's hard to see. So be careful with your minus signs, but the actual equations should all be very familiar to you. All right. So those are rotational kinematic equations, the definitions of rotational quantities. Okay. In the next video, I'm going to show how to rederive circular quantities, all the stuff we've been doing, and all the centripetal acceleration, everything. And I'm going to do it, I guess, in a slightly more sophisticated fashion than what we've seen. I'm going to introduce polar unit vectors and kind of work through the vector calculus a little bit more carefully. It's not something that you really need for physics 1, but you will need to be able to do it. It's the kind of thing you do more next year. So if you're going to take dynamics in particular, or I suppose maybe Calc 3 might have some problems a little bit like this too. So anyway, next video is going to be a little bit more of a math background for these kind of problems.